Welcome back to Curious Conversations. My name is Shreya, and today we have with us the eminent Dr. Vincent Weidlich. How are you doing today?
I'm great, thanks. I just have to say, first of all, that I'm not a doctor yet, actually. So I just to make sure that nobody assumes that, but I will be doing that fairly soon. So nice to meet you.
All right. Well, yeah, of course. Thank you so much for joining us on Curious Conversations today. So, today we're going to be discussing one of your new papers, Artificial Intelligence in Medicine and Radiation Oncology, which was recently published in Curious. But before we get into this paper, I'd like to take a step and examine your background and your pathway to your current position. So, can you walk us through that real quick?
Yeah, sure. So I started off with physics and maths when I was I guess, a kid. My dad taught me a lot of, well, most of it that I knew at that point. I did search out a few things when I got into, became a teenager. I was interested in chaos theory and these sort of things. So yeah, and I was interested in psychology as well. And then later on, I went to uni and did actually business, and then I went into psychology and in artificial intelligence. And now I'm more focused into actually BCI, LLMs, neuroscience, and that sort of thing, and also biohybrid stuff. So,
Very nice. And PCI is, of course, a very big thing in the current, artificial intelligence status quo. So, very timely topic in conjunction with neuroscience. So, going off of your paper, at the start of your paper, you talk us through a wonderful story about a modern hero of technology, Alan Turing. Could you start by
yes.
discussing that story and its applications to your paper?
Yeah, so a lot of people, I guess most people would consider him kind of like part of the beginning of AI in general. I do believe that he actually changed the game, if that makes sense, for the whole computer science. So a lot of people refer to him as kind of morally, basically a basis for the morally sound part of AI. Also, I think that since there's a lot of dispute against AI, if you could say that right now, which is and also for a while, honestly, it's always important to remember that it can be used for something great, just as any tool in science has its negatives and positives in terms of its use. So that's kind of how that was going.
Yeah, of course. And so, jumping into the usage of AI in medicine and specifically radiation oncology, can you discuss what it's been like in the status quo then and what the limitations of this usage have been like in the past?
Yes. So it's AI is not so much. I guess you could say until recently, it wasn't so promoted hard for getting, I guess, catching on in terms of medicine. It happens a lot of the time where people are kind of fighting back AI to take their jobs, honestly, because a lot of people are afraid of that. It's understandable, of course, but at the same time, now that people have gotten used to it more with things like ChatGPT, I think people are a lot more open to it, and that's now we're seeing a lot of growth with generative neural networks, for example. Those are very important for medicine, and as well as let's say simple linear regression, deep learning, feature extraction and engineering, and that sort of thing. So it's catching on a lot faster now than it did before. That's for sure, and that's partially due to I think sort of like the majority opinions of AI, and also due to the tech itself that's been advanced.
Yeah, absolutely. And so, building off of that, I guess, how did your paper build off of the status quo usage of AI? And could you go ahead and walk us through your paper?
Yeah. So instead of going through the whole paper, what I could do is actually just summarize different parts of it. Basically, uh, we as humans, we are prone to errors, just as any other system has errors. But humans have a little more errors in that sense, where when we transfer information, a computer usually just copies and pastes, and it's pretty simple. But for us, there's usually some sort of error in that, or not every time, but there's definitely a higher percentage of errors. So that's something actually that when we deal with data, if it were to be automated, putting one data here and taking it from here, these kind of things, that would decrease data errors in terms of transfers, but also in terms of, let's say, calibrations of machines. You could also go to even as far to say that the treatment itself could be better with machines, because although scientists and doctors and everybody involved have a lot of inputs into I mean, people have experience and everything, but machines ultimately can do what humans can do if we train them to do it with the right type of algorithm. So it's a case of trying to figure out, I guess, how to decrease the errors and the problems that humans are creating, but at the same time allowing those same people to kind of still work in that field and still have to be somewhat of relevant, I guess you could say. And that it's difficult because there's also risks. Liability is something that commonly comes up, although honestly, I think it's a little bit it's actually more certain than not. Liability has always been something legally like kind of putting it off to the next company, if that makes sense. So like if there's a large company and they have machines and those machines have parts, each company involved in the service that the machine gives or product, it has some form or not of liability depending on the contracts that they've signed and this sort of thing. So AI is the same thing basically.
Yeah, got it. And so, given all of these different factors that you just mentioned, what do you foresee as the implications of AI's usage in radiation oncology? Do you foresee that it's going to be widely accepted?
Uh, yeah, I do. I think that it's already making its way in there, and at this point, it's more of a question of how it's going to be accepted. I guess you could say that because there's a lot of I guess you could say the the strategy of implementing the AI into the actual treatment planning or into calibrations or into R&D and these sort of things. That's uh, there's a lot of red tape around that, if that makes sense. Like, and there's a lot of regulations. I think that that's really important to kind of figure out how to incorporate AI the right way, responsibly, ethically, but also efficiently, if that makes sense, and not to kind of like wall out AI just because whatever reason they might have, if that makes sense.
Great. And then, in your sense, I guess, what work do you have planned for the future?
Yeah, so for the future, I really I want to work on uh, basically connecting the human brain or organoids and kind of brains to silicon or classical computing. So, for example, you could have a computer that's like the classical computer that you usually think of, connected to a sort of biological computer that you could say that. I mean, it could be your brain could be involved as a sort of control unit, and then that would basically control the computation and also the BCI aspect in terms of the interface. That would be, I think that's a big problem, but it's not a problem that we can't solve. There's, for example, been work done with electrodes and neuroprosthetics and giving people vision, and that's kind of the direction where we have already been going. But also there's such things like using bacteria as neural networks and kind of connecting things in a sort of more biological way. So I think that if we're able to, or when we're able to uh, balance biology and like silicon computing and get that to be uh, working together the best way. I mean, we could do a lot of stuff because the brain is by area and by energy, it's the most efficient. It's a way more efficient than any supercomputer in terms of most of the stuff.
Wow, okay. Yeah, I'll definitely keep an eye out for this when it comes out. This is very fascinating things. What specifically are you planning on doing, like, with the integration?
Yeah, so right now I'm focused more on chaos theory and dynamical systems theory, applying and quantum inspired mathematics and applying that to EEG and trying to figure out exactly how to predict things and how to, closed loop stuff. So how to know what to do to and predict what's going to happen to simplify it in the brain, and that can be really useful for many stuff. For example, if you have let's say a system where you control something, you have an input and an output. So the input needs to be sort of regulated also, and the output of course actually is a lot easier, honestly.
Very interesting. All right, well, thank you so much for joining us today on Curious Conversations.
Thank you too.